Good morning, and it's great seeing all of you here, and thank you for coming to the session. I'm Ted. I'm a program manager on the Azure Machine Learning team, and Doug here is a distinguished engineer in Microsoft Research. And I think you've heard a lot about the announcements yesterday with Project Brainwave, and what Doug will be going through will be a deep dive into what Project Brainwave is, and then I'll talk about how you can use Project Brainwave. So we'll start off with Doug, and just giving you an overview of Project Brainwave and how you can use that to accelerate everything.
Great. Thank you, Ted. Good morning, everyone. Thanks for coming. So we're going to do 25 minutes for my half and 25 minutes-ish for Ted's, and this can be interactive. So if you have questions at any point, feel free to put your hand up. We have enough time, I think, to have some online discussion. For those of you looking at my right eye and wondering what happened, it wasn't a bar fight and it wasn't a technical disagreement. I'm a squash player, and I took a racket to the face Saturday morning. Unfortunately, I had protective glasses on, so there's no problems here, but it does look a little grim, although it looked a lot worse Saturday morning. Okay, so this is a really exciting moment for us because we are taking this work that we've been doing across the company to accelerate our internal AI and bringing it to our customers. And so, I run a team in research that built a big chunk of the Brainwave architecture, which runs on top of the FPGA infrastructure that we've built. And Ted is the product owner that's really running the service. And so really, Ted is your right point of contact. I'm always happy to answer questions and forward email to Ted. And since he's the hard product truth guy, he's going to give you some serious technical depth. I was a professor for 10 years, and so if I flip into professor mode, Ted may come up with a hook and pull me off. Okay, so what is Project Brainwave? It's a hardware architecture. Think just like the NVIDIA Volta, Google TPU, Nirvana's chip. There's about a zillion startups building their own, what we call NPUs for neural processing units. So Project Brainwave is a hardware architecture. The reason we call it project is because we don't have an official product name for it yet. So it's still in the research project nomenclature phase. And so we've chosen with the hardware architecture to synthesize it down to FPGAs rather than building our own custom chip. And that's a deliberate choice, and we think, at least at this point in time, it's been the right choice for us, and it's given us a tremendous amount of flexibility and also the ability to get into a performance leadership position for DNN inference. And we've had a great collaboration with our partner Intel, who's been working with us to optimize the system, and we've really benefited from their technology. So I know I have a bunch of friends from Intel in the room here, so thank you all for the great partnership and support. So I think what I'll do to start off is play a short video that we had produced, and to give you a sense of our overall FPGA project and really what we've done over the past few years. It's been a really interesting ride because we've been able to leverage this for all sorts of different data center workloads. Project Brainwave is the latest attempt or the latest iteration that drives it for deep learning. And so let me start with that. And then we'll continue.
In this era of exponential data growth, data centers need a faster, more intelligent cloud to keep up with growing appetites for compute power. Since the earliest days of cloud computing, Microsoft has been innovating with specialized processors to give CPUs a boost for critical workloads. Among accelerator options, FPGAs offer a unique combination of speed and flexibility, ideal for keeping pace with rapid innovation. On FPGAs, data flows through programmable silicon-level logic blocks that process instructions in parallel, a perfect approach for big data. Our unique board-level architecture uses Intel FPGAs to augment our data center with an interconnected, configurable compute layer. Microsoft leads the industry in transforming data centers with programmable hardware. We were the first to prove the value of FPGAs for cloud computing, first to deploy them at cloud scale, and first to use them to accelerate enterprise-level applications, beginning with Bing. Our leadership in accelerated networking delivered the world's fastest cloud. Our pioneering with FPGAs for distributed computing paved the way for breakthroughs in artificial intelligence. our FPGAs enable real-time AI with industry-leading price for performance. And this is just the beginning. Microsoft has an aggressive roadmap of platform, architecture, and algorithmic innovation ahead. Azure will remain the world's most intelligent cloud.
Okay, so that's a little bit of the project history, and I think you saw from 2016 to 2018, we were building a lot of this AI capability onto our network of FPGAs that we've provisioned within the company, and really what the announcement today or this week has been is about bringing that to our Azure customers. And so I'll talk a little bit about the architecture and why it's disruptive and how we generated these levels of performance, and then Ten will go into what the service looks like, how you can access it. I think one thing that's really important to understand is that when you work with raw FPGAs, people typically write something called HDL, which I'm sure many of you have heard of, hardware description language, in a language like VHDL or Verilog. And really these are languages where you code like you're designing a chip. And then you will take that hardware code and run it through a different tool chain or a different compiler, a hardware compiler. And then you can either take that to a fab and produce your own custom chip, or you can run it through a different flow and synthesize it onto an FPGA. And of course, the FPGAs, you can change the image every second if you want to, although it's hard to generate programs that fast. And so what's really nice here is that we've built an engine, that's what Project Brainwave is, that has its own language, so we can write down to it in a higher level language. Right? So when you have a DNN, we can work with customers to map that DNN to the engine rather than dropping all the way down to the bare metal of the FPGA. So it's a much easier developer experience than working with the raw FPGAs. In some sense, we're abstracting the complexity of that programmable hardware chip from our developers and users. But the really nice thing about that model is that we can actually keep turning the engine and turning the crank and improving that hardware continuously under the hood. Almost like you get a new, like when you're using CPUs, you get a new optimized CPU every month without actually changing the chip in the socket. So as we generate more optimized versions of the architecture, we can slide those in, and they'll remain software compatible with the models that you port. And so you just get this continually improving level of performance. I mean, Ted knows that we brought up the convolutional networks, the ResNet 50 model that's our launch offering, and 3 or 4 weeks ago, I think it was maybe 10 times as slow as it is today because the team was just tuning it, and they brought the latencies down until we're now at about 1.8-ish milliseconds per image. And so as customers, you'll see those improvements come in a steady stream. We rev the hardware more than once a month. And one of the really neat things about that model is that when there's a discovery in the deep learning community, so we see some research paper published with some new operator, some new activation function, some new algorithm that's substantially similar but different from what we're currently deploying, we can actually pull those innovations in very fast and then roll out a new image. So it's like your hardware infrastructure that are running the models in your enterprises, for those of you who are enterprise customers, will have a steady stream of advances following closely behind their discoveries in the research literature. So it really keeps you up to date and keeps you in a super compelling position. All right, so I'll go on with a few more details here. I don't think we want to see the video again. Okay, so we talk a lot in this release about real-time AI, and I'd like to be very precise about what that is. So I think many of you know this, so apologies for the redundant information. What many chips today do that in the DNN acceleration community is something called batching. And the idea behind batching is you take n requests, where n could be 2 or 4 or 8, or 256 or 512 or 1024. It doesn't have to be a power of 2, but it often is. And you lump those individual requests together into one big batch or package, and then you ship that off to the hardware all at once. And the reason that works with a lot of the chips like GPUs and TPUs today is that the chip doesn't have enough memory bandwidth to keep one request busy. So you get low utilization of the chip if you only send it a single request. So by sending it 1,000 requests, the chip can work on the first chunk of each of the 1,000 requests, and then the second chunk of each of the 1,000 requests, and then all 1,000 finish at once. The aggregate performance you get out of the chip is thus much higher, but the latency you see is actually much lower, or much higher. It's much slower. And so today, typically people have to make a trade-off between, do I want to run with low latency, or do I want to run with high throughput, which means low cost? And so what we really tried to do with this real-time AI model is eliminate that distinction. And so we got rid of batching. And so the chip runs at nearly full throughput with a single request. So you send one request to the Project Brainwave service. The chip gets very high utilization, and it sends you the answer as soon as it's processed. And then you can send another request. And so in some sense, you're sending a stream of individual requests, and you're getting a stream of responses back. And so you don't have to play games in software where you're batching up 1,000 separate requests, waiting for them to arrive, batching them together, doing the data marshaling, shipping that whole big package over, then waiting and getting the results back. So it really simplifies the way you use this system. You don't have to think, well, what's my latency bound? How much should I batch? How much will it cost me to do that? We just say we provide a single interface. You just send requests as fast as you can, and the responses come back really fast. And that's really what you want in real-time scenarios. When you're on we've talked about Jabil as our lead customer, or one of our lead customers. They have a manufacturing line. They don't want to see 256 boards fly by on the manufacturing line before they ship the images off to a DNN to be processed and figure out which of the boards are bad, because by then they're down and way down the line in the next stage, being incorporated into products, right? So they send they look at the circuit board, they send an image, it comes back good or bad. If it's bad, they pull it off. If it's good, it keeps going. And they can keep up with the rate of the line. In fact, they can speed up the line now because of those capabilities. So for deep learning, the deep learning is starting to cover many, many areas. And initially, it's being integrated in workflows for things that are pretty common in terms of people's capabilities: vision, language, speech, question and answer, knowledge. But what's happening more and more is, as we're discovering new uses that humans aren't good at, those are a little bit harder to find. Things like sales lead generation, malware detection, bug finding. There's just many, many, many applications of deep learning that we're discovering work well that we just didn't know because we haven't evolved to process those workloads as humans the way we had with speech and vision. And so these capabilities are growing and becoming broader and broader, and we're seeing them get incorporated gradually into many of Microsoft's products, and our competitors are doing the same thing. And then it turns out that many of these use cases end up being real time on inference. And so if you're having an interactive session, or you're integrating with some live process like a manufacturing line, or you've got 1,000 cameras in a retail store, and you want to know what's happening at any given point. Is somebody shoplifting? Is some product out of stock on the shelves? Has a refrigerator door been left open? These are all things that you want to find out as soon as they happen. And so that low latency is really critical. And by eliminating that trade-off between cost and speed, we can now integrate real-time AI into our processes with really no consequences or no trade-offs. So we think it's a pretty exciting offering. Now, previously to this release, the DNNs have been pretty constrained by performance and power, which is why we're starting to see all these new accelerators be generated. And because these accelerators tend to be pretty memory bound, like I said, that's why you have needed batching up until now. But with this release now, we can give you a hardware accelerator that you can get real-time AI on, get your responses quickly, and get very, very competitive cost. So really those trade-offs go away. One other interesting thing that we've announced, and I'll touch on this a little bit later, is that we're going to do this both for the cloud and the edge. And so a lot of customers have real-time flows in their factories, in their warehouses, in their oil platforms, in their oil wells, in their ships, in their drones, in their airplanes, in their office buildings. I mean, all of these things have servers, and very often, the data you're processing is so intensive, you don't want to send it all the way to the cloud, or you don't have time to send it all the way to the cloud. And so that's where real-time AI on the edge, and here in the edge I mean in servers that are on customer premises, is really important. There are also scenarios in the cloud that people care about. Like when your big data sets are in the cloud, you've got multiple data sets streaming in from multiple places, like think satellite imagery, and you want to correlate that with other events. And so there's definitely real-time uses in the cloud as well, but there's also a lot of real-time uses on the edge. And so when we developed this capability, we thought it would be really important for customers to have both. Now, the cloud offering is a little bit ahead, so we have people in production today, thanks to the great work of Ted and his team. And we are working through the details of the edge offering, but we are in preview and we are working with partners. So now, I'd already talked a little bit about why we chose FPGAs rather than synthesizing a custom chip, but I want to go over those advantages again, because there's a lot of noise in the community. I mean, there's startups that have raised hundreds of millions of dollars, and so they really want, they're talking about high levels of performance, and there's a lot of one-upsmanship with metrics and benchmarks, and just a lot of chatter because the economic stakes are so high. So I really want to cut through that. And so the first thing we did with the Project Brainwave architecture is said we want to do this real-time thing, so we're going to get rid of batching. And that means you both want to have the high throughput that I mentioned and very low latency. And so performance, there on the left, was one of our primary goals. And so what we've been able to show is that we have industry-leading latency for the requests we're sending over to the FPGA. So the launch model we have is ResNet 50, which is a general image classifier, a very popular image-based DNN. And of course, we're working with lots of partners on other models, and we've got a whole ton of models within Microsoft. And so we'll be rolling these out in pretty rapid succession. But on ResNet 50, no one has actually shown levels of performance at any batch size comparable to what we're achieving on FPGA. And right now we're hitting about, from a local host to the chip and back, about 1.8 milliseconds per image. And that number is continuing to drop. There was a little bit of because of all this, the economic stakes and the numbers flying around, people have been pushing a meme that, well, if you build a custom chip, it's going to be faster. And they talk about ASICs, application integrated circuit, which people typically think of as being very efficient because they only do one thing. But it turns out that all of these DNN accelerators are actually programmable. They're all programmable engines. They all have an architecture that you can program to because you want to run different models. And that programmability comes at a cost. You want to be able to do multiple things, and you need to make design choices when you build the chip. So TPUs, GPUs, other NPUs, what I call neural processing units, coming in from all of these startups, and the Project Brainwave engine on FPGAs and other neural network implementations that people are doing on FPGAs are all examples of programmable accelerators. And really, what you have to look at is the architecture at that top layer, not what is your deployment strategy, is it FPGA or custom chip or something else. And so what we've shown here is that we're able to achieve industry-leading performance with the FPGA by choosing the right architecture. And a lot of people had thought that that wasn't possible, but I mean, I think that a lot of that is just misconceptions and fun. Okay, and then I talked a little bit about the flexibility in that we can incorporate new discoveries quickly, we can tune the engine continuously, so you get this rapidly improving stream of innovation, really without changing your software model. So we port a model, and then your engine gets better and better over time. Now, of course, we can do things that break the architecture if we get radical improvements, and that's always a discussion with customers. It's just opportunity, but we will support backwards compatible models. Another really interesting thing that we do, though, and this is something that we haven't talked about very widely yet, is that these DNN models are actually very different. A convolutional network for image processing is very different from a recurrent network for, say, text processing or language processing. And there are many different kinds of networks now coming out of the research literature. These different networks actually have different requirements. And so what we do in the Project Brainwave system is we will actually generate images of the hardware accelerator that gets mapped on the FPGA that are customized for individual models or classes of models. And so if you have 4 big buckets of models, we can actually generate 4 variants of the engine that are tailored and streamlined to those models, as opposed to giving you a single fixed architecture that has to serve all types of models and where you have to make design compromises. And you have to pick those when you freeze the architecture And then that has to work for 2, 3, 4, 5 years. So we're able to shrink wrap the engine to fit models. And in fact, we even do things like pick the data types. Instead of 32-bit floating point or 16-bit floating point or 8-bit integer, we actually might pick 9-bit floating point for this model and 8-bit floating point for this model. And that all happens behind the scenes. We have in our tools, we have a flow, right, that will take your models and cast them into the right data type and then pair those with an image of the project brainwave architecture that's been optimized for that model. So when you think about the edge offering, what you want to do, and I know we'll get into the details later, but you'll be running an Azure IoT Edge client on the server. It will connect up to Azure ML where you've trained your model, and it will pull down both your model and a version of the Project Brainwave engine that's been optimized for that model. And so really the FPGA images that implement that architecture and the models are paired tightly together. And so you can optimize it on a per model basis. That's a capability really that very few other offerings have. And that will also give you another boost in efficiency up beyond what we're doing just with the raw architecture and the real-time AI and the elimination of batching. And then finally, in our cloud, for the cloud offering, we have scale. So Microsoft has been putting one of these FPGA boards in just about every new server it buys for 3 years. So Azure started in 2015. Bing has been doing this in about the same time frame. And so we've deployed massive numbers of these things. We have more scale than anybody else in the industry for this technology. And so there have been some demos this week. The Esri demo in AI for Earth, where it's been shown already, right?
Mark Rusinovich will show it.
Oh, okay, all right. So I won't give it away, but should I say it? Okay. Well,
go to Mark's talk.
Yeah, go to Mark's talk and see the demo. But that emphasizes the very large scale at which we're operating. So for customers that want to integrate very cost-effective real-time AI into their businesses, at the business site, we can do that. Our offering will do that. If you want to go into the cloud and intersect flows and do AI on those flows, we can do that. But then if you want massive scale, we can also do that. And that's one of the other advantages of the cloud. You get massive scale and that elasticity. So if I want to be processing hundreds of millions of images in a very short time frame, we can scale out and get that job done for you. And so that's a really compelling capability that I think we're just even now starting to understand what that really means, because there are all these big data sets, but people haven't been able to operate at this scale and these speeds before. So it's going to make new things possible, like just continuous monitoring of very large data sets, very large facilities, geographic regions. Think about the power grid and what you might be able to do there with millions of producers and millions of consumers, as opposed to a few centralized producers like coal plants that you can move up and down. So just this worldwide scale is an opportunity to really start building control systems, but you need very large scale to run those control systems with AI, and that's something that we offer. Okay, and then we don't really talk about cost compared to all the other technologies because there's a base cost and there's margin. What we've just been talking about is the cost to you, the customer. And so when you come to Azure for this offering and you want to get on Ted's service, his team's service, and start classifying images for your business, for your research, for your personal life, whatever, the current cost of the current offering is under 20 cents per million images. And so that's what it costs you to rent the service, process 1 million images. You'll pay about 20 cents, actually a little bit under. I know it says 21 on the slide, but because we've been tuning the engine, the costs have come down because the throughput has gone up since we made the slide. Okay, and I'm hopeful that in a few weeks it'll be 16 cents and then 15 cents. I can't keep up, so we're just going to leave it at 21 cents and speak to it. Okay, and actually I do think, Ted, we're going to be at 15 cents in a few weeks, a month. Okay, so that's also a really amazing thing, and this level of capability hasn't been available before. Go ahead. So the low cost is at, okay, yeah, so the question, I'll repeat the question for everyone. The low cost is at what latency? And it's a little bit of a nuanced answer, so I'm going to give you an honest answer rather than a marketing answer. So the low cost is at that real-time AI batch 1 offering. Okay, and so today from the service hosting the chip, like I said, it's 1.8 milliseconds. Currently, we haven't tuned the software stack as much as we might, so it's still a few milliseconds over to that server and back. Okay, so we're seeing today 6 to 7 milliseconds end to end. And we also haven't tuned the flow of images. So if you're using all 24 cores, for example, on a host machine, driving all that data to the FPGA and then back, there's a bunch of queuing delay in that host machine that's driving up another 10 milliseconds. So there is actually some additional latency when we're driving at very high throughput, but that latency is not fundamental, and we're going to be driving it out over the next few months. So for example, like the time to the server and back is going to go to near zero because we have this accelerated networking capability. And I might be getting over my skis, but I'm going to keep pushing on that. I think the marketing answer, which is also true, is that at that cost, there's no inherent extra latency built into the system. So it's still that industry-leading latency of the chip. It's still batch size 1. It's still real-time AI. That's all true. Just today, when you're driving it at maximum throughput, there's a bunch of queuing elsewhere in the system, not on the chip itself, that's adding some latency. But that's going to come down over time. Okay. So like I said before, really what we want is no compromises. We want to give you real-time AI, very high performance at that cost structure, which is continuing to drop. And I'm confident we'll get there. And it's already really good. Ted, do you want to add anything to that?
Yeah, so I think the question from latency, like Doug said, if you were to send an image in the same data center as the FPGA, we're seeing about 6 milliseconds end to end. So basically, the service offering is about 42 cents an hour. And to run 1 million images takes about 31 minutes. And that's where we're coming up with that 21-cent mark. Yeah.
And it's continuing to drop. I have to keep emphasizing that because our team has been burning so hard up till build. Right? Every cent we're squeezing down, I get excited by. Right? It's kind of a sad life. Okay, so I think I've actually talked to a lot of this. I'm going to say a little bit about our internal technology because we don't have it quite ready for the public offering. So today, what we've deployed in Azure are servers that have 4 of Intel's really amazing Aria 10 FPGAs on individual cards. Okay, so that's a fairly standard high-end server, and it's got 4 of these cards. You've already heard the price structure to rent a single FPGA VM. Of course, you can rent multiple ones if you want more throughput, multiple boxes. What we've actually built within Microsoft, and we haven't brought this technology to customers yet, but I want you to see where it's going. And you saw it in the video, is this notion of a configurable cloud. So what we actually do within our infrastructure is the FPGAs talk directly to the network. And so they are network-attached devices, which allows us to scale out with very low latency. And so what you can see here for very large models, and this is something we do in worldwide production today already, is if we have a really large model, we'll take it, and then we'll just stripe it across those Fs there, those FPGAs that are talking to the level 0 switches in the data center up to the level 1 switches. And so this is something that aspirationally I would like to bring to our customers, because then you get the ability to run even larger models at even greater speed. So I think the point of this is that we do have a roadmap where there's some very advanced technology coming down the pike. We just have to figure out the cadence to get it into Azure and bring it to our customers. And then, of course, on each FPGA is that Project Brainwave hardware architecture that's synthesized down onto the programmable hardware that you can see over there on the right of the chip. And so we've talked about the speed and this trying to eliminate this trade-off between cost and latency to first order, although we still have some tuning to do. And we've talked about the flexibility, which is another advantage where you get this continuous stream of updates and improvements, and you also get the ability to customize the engine for different models, which gives you an additional bump of efficiency over what you're able to do with other technologies. And then the last point that I really like to emphasize, and I think you've hopefully heard this, is the fact that we want to support many of the frameworks. We want people to use any framework that's popular that they bring to the cloud. And so we're doing models in TensorFlow today. In fact, we'd like to run TensorFlow in lower latency than Google does with TPU. I think we're already there. But we want you to be able to bring CNTK, PyTorch, many others. And then we have this open source, Open Neural Network Exchange, ONNX format that we will also be supporting. And so the idea is that many people in different frameworks will be able to party on this infrastructure and get great benefits without being locked into a vertical. Yes, question in the back. So the question was, do these ASICs become more cost efficient than the FPGAs? And I think maybe I'll use that, and I'd like to address that question now because I think it's a really important to address. So I'm a long-time computer architecture researcher, and I'm actually a CPU architect by training. So maybe this is a new adventure. But if you want to be sort of academic and nitpicky, ASIC, and I'm sure you know this, many here may not, it stands for Application-Specific Integrated Circuit. And typically what that means is a fixed pipeline that only does one thing. All of these neural architectures that people are building, like I said before, are programmable architectures. And they can be synthesized. They're not really ASICs. They can be synthesized down to a custom chip, which is kind of how people are using ASIC today. That's become popular, or an FPGA. So now, if you decide, hey, here's a neural processing unit, NPU architecture that I want to run at very large scale, and I'm synthesizing to an FPGA, but I'm convinced it's not going to change, and that the models, the class of models that it supports, as opposed to the other variants, is so big that I want to optimize it for cost, I might be willing to pay the $50 million and stamp out a hardened version of that, where the area is slightly lower. You can always take something soft, synthesized on an FPGA, and make a more efficient copy, although you have to freeze the design, and it takes several years to do that and get it in deployment, and it costs some number of tens of millions of dollars. So there are scenarios where I think this makes sense, and but at least for us, every quarter we ask ourselves the question: is it time to maybe take one of the engines of the many we synthesize on the FPGAs and harden? We haven't hit that point yet. We're still iterating it pretty fast. So in theory, it's possible. But right now, all the economics say, no, this is the path we're on is the right one. And really, we're at, I think, a very strong performance leadership position in the industry while retaining all that flexibility. So it's a pretty good place to be. Yeah. I mean, I think what really matters is the architecture you pick above that custom chip FPGA deployment vehicle. And so I'm just, as an ex-academic, and Ted, you might want to stop me when I'm running over. I don't know how we're doing on time. 5 minutes, okay. What's really fascinating right now is that all of these different designs that people are building are all fundamentally different architectures. Brainwave is actually a sort of an out-of-order vector data flow thing that looks under the hood more like a superscalar made of vectors, but at very much wider ILP or VLP. The other startups have massive numbers, thousands of statically scheduled tiny processors, so all the smarts is in the compiler. Google's got a systolic array. I mean, there's just, all these old debates we had in the 80s about, it's all being replayed now for neural networks, and no one knows what the right answer is. So the people that pick the right architecture are going to do well, regardless of how they deploy it. Again, but we're iterating and learning very fast, so I'm pretty optimistic about where we are. Okay, so we talked about scale, so I'll skip over that. And I think this is slide 15, isn't it? One more. Okay, well, I'm going to turn it over to Ted because I think this is where he can pick it up. Okay, cool. So I got done 3 minutes early.
Thanks, Doug.
All right.
This is the first time you've seen it, 3 minutes early. Saw it here first. Thank you, Doug. I'm Ted, so I'm a PM on the Azure Machine Learning team, and Doug essentially described to you the engine of a Lamborghini. You think about it that way. And it's a beautiful engine. It's superly highly tuned and optimized, and it just hums. But it's an engine. So from the product team, I'm here to give you the keys to that Ferrari and show you how you can drive it. And so in terms of Project Brainwave, as we talk about, the first thing is just ResNet 50. And so ResNet 50 is this deep neural network. The way I like to think about deep neural networks and how they can be flexible is in the context of a bomb-sniffing dog. So let's say you wanted to train a bomb-sniffing dog. At the end of the day, a bomb-sniffing dog is a German Shepherd. Right? So imagine you have a 3-year-old German Shepherd German Shepherd has the infrastructure, if you will, to be able to take in smells and to be able to distinguish among smells in a very, very sensitive way. So that's what a German Shepherd is good at. But a German Shepherd is not a bomb-sniffing dog. So what do? You give it some smells. You say, this smells like a bomb. This doesn't smell like a bomb. This smells like a bomb. This doesn't smell like a bomb. 3 weeks later, 20 boxes of kibble later, you have yourself a bomb-sniffing dog. So training that German Shepherd to be a bomb-sniffing dog is not that difficult. Building the German Shepherd, that's the hard part. So essentially, ResNet 50 coming out of Microsoft Research is this German Shepherd. So when we launch with ResNet 50, now you have the capability of having a German Shepherd that would be able to take in data, image data in this case, take out those features, and then to be able to train those features to do the things that you want to do. So as with a German Shepherd, now you have a bomb-sniffing dog. Now you have a food-sniffing dog and a fruit-sniffing dog for your airport. Now you have a skin cancer-sniffing dog, right? All these different things you can do. So, I can't emphasize enough for Doug and his team the kinds of world-class researchers we have to be able to do that industry-leading performance. And so in terms of what we have from the Azure Machine Learning integration, I think also Doug talked about no batching required. I'm going to now talk about what that looks like from Azure Machine Learning.
Connecting with people from different cultures. Finding and treating cancer earlier. Making the world accessible to everyone. Today's breakthroughs in artificial intelligence come from deep neural networks using very large, multi-layered models that need amazing amounts of computing power. Running these models at high scale, low cost, and ultra-fast speeds has always been extremely difficult. Not anymore. Project Brainwave unlocks the future of AI by unleashing programmable hardware using Intel FPGAs. And this delivers real-time AI at blazing speeds with no batching, no compromises, and no need to choose between high performance and low cost. Azure Machine Learning Accelerated Models, powered by Project Brainwave, enable data scientists and developers to easily train deep neural networks and deploy them to the world's largest configurable cloud with record-setting performance. ResNet 50 is an industry-standard image classification model. Processing one image requires nearly 8 billion operations. Project Brainwave leads the industry in speed on ResNet 50 models with under 2 milliseconds per image, with image classification that can be customized with your data. Jabil, one of the most technologically advanced manufacturing companies on the planet, maintains rigorous standards of quality control. Today, Jabil identifies manufacturing defects in electrical components using human judgment, one set of photographs at a time. What if Jabil could analyze thousands of quality control images in seconds, using deep learning to reliably identify anomalies for people to examine more closely, making humans more effective and making the whole process faster and more accurate? Now they can, by using Azure Machine Learning Accelerated Models to train and deploy a model, whether in the cloud or on the edge. What can you build with accelerated real-time image processing? Detect spills or open freezer doors in your retail store. Conduct real-time medical image analysis. Inspect critical equipment. Track endangered species. And this is only the beginning. Accelerating with programmable hardware means Project Brainwave can evolve quickly to keep up with rapid innovation in deep learning. Microsoft is already using many models for text, audio, speech, and natural language, and will bring these models to you soon. You'll even be able to accelerate your own custom models and design the next generation of real-time AI applications. Start accelerating with Azure Machine Learning and Project Brainwave today.
All right, so let's talk a little bit about Azure Machine Learning and in terms of how it can integrate with Project Brainwave. So Azure Machine Learning is an end-to-end data science platform. And you think about what data scientists do today. Data science is the sexiest job of the 21st century, but you talk to a data scientist and they're probably spending 50 to 80% of their time on very boring tasks like data cleaning and a lot of data janitorial tasks. So starting with from an intelligent data preparation perspective, just having tools to be able to help you get that data into a cleaner form that then you can process. In terms of model training, giving you the flexibility of training your model on the compute that makes the most sense to you. Maybe you want to train a model very quickly on your local workstation, trying out different models and trying different frameworks just to see how you're able to get something that seems to be promising. You want to do that quickly on a local machine. Then you might want to scale up to a Spark cluster, maybe run a cluster on CPUs. Now submit jobs to this big cluster that then you can train on to be able to train your model. Maybe for deep learning models, you want to spin up a GPU cluster using something like Azure Batch. So now you have a GPU cluster, spin up, submit your job to train, and then spin down again. So the integration of all of these various compute contexts, and now recently with the integration with Databricks too, to be able to train these models very, very quickly. From a model management perspective, this is also starting to be very important. We were talking to the CIO of a Wall Street firm, and he was saying, we have 10,000 machine learning models in our firm. We get data from them, we make decisions from them, but I have no idea who created the models, I have no idea what their training results are, no idea of the performance. So what happens in that situation? So it'd be great to be able to get the results from a model, trace that model back to the source code, know the data scientists that created the model, know the training results and all of that. So that's becoming very, very important from an enterprise perspective. We bring in the best of open source. So whether you want to use Python, Microsoft Cognitive Toolkit, Google TensorFlow, Caffe, all of these different frameworks you're able to use in Azure Machine Learning, because we know there's so much innovation happening in open source to bring you the best of open source. A lot of great features and functionality in open source, which is great. But some of the things that open source does not care about are the boring things like compliance and security and VNets and all those things that an enterprise cares about. So what we do with Azure Machine Learning is that we give you the best of open source, the best of Microsoft, and then we package it up into an enterprise-grade end-to-end data science platform for you to be able to build and train your models. And so the preview offering for Azure Machine Learning hardware-accelerated models is incorporated into this entire infrastructure, into this entire platform. So the same platform that you're using to train your models, deploy to CPU, deploy to GPU, deploy to the edge, you are now integrating to be able to now also deploy onto an FPGA. So, so this is Python, this is TensorFlow, and then you're creating that model and then deploying it in a serverless architecture. So from an infrastructure perspective, just to give you a quick overview, our first region is East US. So East US is what we're offering with a launch. If you were to deploy a model today, it would be in East US. Each of these stamps have 20 racks. Each of these racks have a lot of boxes, and each of these boxes have 4 FPGAs. This is like that story. I met a man coming from St. Kitts, and he had 7 wives, and each wife had 7 kids, and each kid had 7 kittens, and how many were actually going to St. Kitts. But basically, this is the number. This is how we basically have all of these in the data center. We're going to be adding new regions very soon in West Europe, Southeast Asia, and South Central US. So these will be coming in the next few months so that you'll also be able to deploy models on FPGAs in these regions. And then we'll expand out from there. In the actual Azure host itself, basically, we have the Intel Aria 10 FPGA. We have 4 of them. And there's a wire service that basically is a thing that programs the FPGA. So Doug talked about this image that you flash onto the FPGA. So today is that highly optimized ResNet 50 image. And then in this host, we have our VM. So this is an Azure VM. Currently, this is available only to us as Azure Machine Learning. So we give you back an API. But we as Azure Machine Learning, we provision the VM, and then we flash the FPGA, and then we give you back that API. So on this VM, we have our VM extension. So when the VM is provisioned, the VM extension would talk to the wire service, and we tell it to flash the FPGA. And then that brain slice image is flashed onto the FPGA. This is the way that we talk to, Brainwave talks through the VM to the actual FPGA, and on top of that runs our Azure Machine Learning. And so basically, then we expose the gRPC API. gRPC is used for TensorFlow serving as just a way that people are able to expose these today. And that's essentially what happens underneath the covers when we give you this API. We also have monitoring, et cetera, and all the goodness that you would expect from an Azure service. The pipeline, which I'll be talking about, the actual model that you're deploying, will be running in the Azure Machine Learning runtime. And so part of it will be running on CPU. So for example, maybe you're pre-processing. You're converting a JPEG picture into tensors. That's going to be running on CPU. And then when those tensors are going to be run on the FPGA, that will go to Brainwave, which will then process that on ResNet 50, on the FPGA for ResNet 50. And then you might have some post-processing. So once you get the extracted features, you're going to be running that classifier, and that classifier then runs back on CPU. So the idea here is we have highly optimized operators that can run things on CPU and FPGA, and then accelerating that on FPGA. When you actually deploy a model, so basically, again, using Azure Machine Learning, and I'll go through the code and the notebook for this in a minute, but you're writing TensorFlow, you're using Python and TensorFlow, that's doing that pre-processing, converting those JPEG images into tensors, and then deciding where you're going to run the FPGA, and then you might train a classifier at the final stage, and then after that, what happens is this service definition goes to our model management service. And this is the same model management service in Azure Machine Learning today, meaning that if this destination is about to go to an FPGA, great, model management service knows about it. Maybe you created another model, and it's going to be running on a CPU cluster. Model management service knows about it. So in this way, you can manage all of the models in your enterprise. You know which models have been created, and you know where those models have been deployed. So one centralized location to be able to manage your models. The model management service talks to our control plane service. This is the control plane that will spin up and provision that model. And this is just another view of that VM where we have that orchestrator. The orchestrator might run the pre-processing on the CPU, and then it runs the ResNet 50 on Brainwave. And then for a classifier, then you have essentially, again, TensorFlow classifiers that you might want to run. We can also front this with a software load balancer. So right now, in terms of the throughput that we're seeing at about 1.8 milliseconds, we're getting about 530 images per second. But let's say you need 2,000 images per second. So what we'll do is we'll just make lots of copies on these over multiple VMs, and then front it with a software load balancer so that you can get the throughput that you would need. So essentially, this is the architectural diagram of what happens when you click deploy. And I'll show you next that when you run that one line to deploy a model, all of this is happening underneath the covers to give you that API. So let's run to that right now to our cloud service. Oh, okay. Sorry, let me see if I can. Apologies for this. Maybe Doug, did you want to take any questions? Let me try to remote back into my machine while I'm. Yeah. Okay.
I'll just start here and go back.
Okay. So I'm just curious about so you mentioned the architecture makes you differences on approach so that you will use the TPU or you use the Brainwave, another player uses the approach. So it's this time. So imagine the future. What will it be you considering? So we can see the various approach in the future too, or someone.
So let me see if you said that there's a bunch of different architectures like we discussed, and which one do I think is the right one in the future?
Yeah.
Well, it's a great question. I wish I knew the answer. We've taken Microsoft. Okay, the trade-offs are really, I think, threefold. One is how complex is the software interface? And so, for example, if you're providing 1,000 cores and the schedule has to be static, that's one approach some people are taking. you're presenting, it's like the old VLW or Itanium world, but sort of in a much broader sense. It's a very, very software-intensive interface. And those architectures, I'm not a fan of those architectures. They haven't worked super well in the past. But this time might be different. It may be that DNNs, which are linear algebra, are much more tractable for the software to manage. So I'm just kind of waiting to see. The systolic array approach is really a throughput approach, right? So that's not one where that's actually probably pretty good for training, because you can just bang through a lot of requests and work on slices. And then the approach that we've taken is actually Brainwave expose a single thread of control with vector operations. So you have annotated C that gets compiled down to assembly instructions that are vector operations, and then those get taken and broken up into many, many, many sub-operations in the hardware and scheduled on this distributed fabric and run as a dynamic data flow graph. So the advantages of that are that the programming model is pretty simple. The disadvantage is that you need a pretty sophisticated hierarchy of decoders, which we've built and is working. So I mean, you've seen the results. And then another advantage you get is software compatibility. So if I want to roll out a new generation of FPGA or a new image, I don't have to change the program. I can just change the microarchitecture under the hood. And so I don't think we know how wide that can scale. But in the Brainwave architecture, we actually have single instructions that are matrix vector operations that generate over 1 million math operations per instruction. And then those get fanned out to 130,000 parallel units that run for 10 cycles. So we do 1.3 million operations in 10 cycles from a single instruction. Okay, so now I won't say which one is right. Are you good? But I do have my biases, and those are the trade-offs as I see them. Now, if the compiler can schedule all that stuff really well, then you can really lower the complexity of that decoder hierarchy that I talked about in hardware. Okay, and maybe we'll go back to Ted and take a couple of these questions once we're through the demo.
Okay, cool. Thanks.
It's a great question, though. Thank you.
All right, cool. So just to walk you through a demo in terms of what the experience will be, we have our GitHub repo. And so when you clone the repo, basically what you can do is run our quick start notebook, and you can set up an environment. Everything is packaged up in a nice Conda environment. And by just creating this and activating this will install all the dependencies for you in your environment that you need. And so next step here is, you can see here, again, just Python, TensorFlow, the image preprocessing. This is where you are defining how you want to convert those images. So basically, we have just a bunch of nodes, and the output of one node and the input to the next one will just be tensors. So you'll be taking your JPEG images or your PNG images or whatever they are and converting them into tensors in the preprocessing step. The next step here is where you are loading a quantized version of ResNet 50. So this super highly optimized version from Doug's team. What this means is that this quantized version of ResNet 50 gives you the same results from CPU and GPU as you get on an FPGA. So now you can featurize your data on CPUs or GPUs. When you're training, maybe you want to spin up a GPU cluster and featurize all your data. So you featurize it with this featurizer. The features will be the same as if they were running on FPGA, so that when you train your classifier, the classifier will be performing very well. And so this is that quantized version of ResNet 50. Moving forward, we're going to be enabling different types of models. So you can think about all the various models out there: NASNet, DenseNet, YOLO, and Inception ResNet, a plethora of models. But we'll also enable more models in the model gallery that you'll be able to bring in. And then after that, you'll be training a classifier. And a classifier is essentially the thing that takes these features, and then you train that classifier. And then we package up all of these into what we call a service definition. So your preprocessing step, the step that runs on an FPGA, and then the classifier, all of this is in a service definition file, and that's what we take. When you deploy, this is just your Azure subscription ID with your model management account. And again, the same model management account that you're using for Azure Machine Learning. The model management account that you're using to deploy models onto CPUs or GPUs, same model management account. Everything is incorporated into this end-to-end data science platform. And here's that one line that I talked about. this create service line right here. And all that we saw in the previous slide, when you click this, when you run this, it's going to take that service definition, it's going to get registered with model management account, it's going to go onto the FPGA VM. That model will now be on that VM. From a client perspective, now that you have this API that's exposed, you can call it. And so here I have a picture of a chip that JBolt might be interested in analyzing. So you think about a circuit board and you think about all the various components of a circuit board and you want to determine whether that passed or failed the inspection. So let's click run here and you can see just how fast it came back. So this is 14 milliseconds, so there's a little bit of overhead, but the time that it takes for this picture to leave my client machine, go to the FPGA API, get converted from JPEGs to tensors, run the 2 milliseconds of ResNet50, those 8 billion calculations of ResNet50, run through the classifier, get the results, send the results back to my client machine in about 14 milliseconds. You think about doing something like this on a CPU machine. We have a similar model running on a CPU. That end-to-end would be about 150 milliseconds, so 10 times faster than a CPU implementation. And so this is just the end-to-end on how you are able to now easily create and deploy this model. And so for those of you who were at the talk yesterday, in Joseph Soros's session, we built an app essentially that looked at the performance of a CPU, running this model on a CPU and running it on a box that has CPUs and FPGAs. So in this case, you'll see that the needle kind of barely moves, but we're getting about 4 to 6 images per second on a CPU. So there's a model. We deployed it on a CPU machine. It's running in the same region as our client app here. And we're sending images. We're using 4 concurrent threads to be able to send images, as many images as we can, to the CPU model. And here's the median latency, and here's the and the throughput is about 6 images per second. So let's now start sending images over to the API that's running the model on FPGA. And so you can see just with one thread, I'm getting median latency of about 6 milliseconds. So 6 milliseconds to go end-to-end from image to API and back again with the result. And the reason that the throughput is actually pretty low is because I'm only using one thread to send one image one after the other. I can't send images fast enough to this API. So let's slam this API and kick it up a notch, or 8 notches here. And you can check out that kind of throughput that we're seeing. So the hit on latency is actually due to, again, what Doug was talking about, those queuing latencies. But if you had essentially 8 machines that were sending images to this API, you would be getting about 6 to 7 millisecond latency and about 530 to 540 images processed per second on that FPGA. So again, this is the type of performance that we're seeing, 42 cents an hour, 21 cents for a million images, right? That's what you get for one chip. And that's everything from our cloud offering. So this is the thing that you'll be able to do when you clone that GitHub repo and deploy your own FPGA service. This is the type of performance that you'll be able to see. So remember that the FPGAs live in the East US data center, so your client machines should also live in East US. Otherwise, the network, just sending images across the network to the API would add a lot of latency there. So now the next thing I want to talk about.
Ted, can I interject
Absolutely.
one comment? So that 6 to 7 that we talked about, is several milliseconds going to across the network and back. And in the video, we talked about our accelerated networking program, which we're actually not using. But we've announced that the VM to VM latency when you use accelerated networking, and we're going to be turning it on, is about 25 microseconds. So and actually, it's actually quite a bit lower than that, but I don't think we're supposed to say that. So it's going to be dropping quite a lot. And so you start to see how with this hardware accelerated stack going end to end, you can just hit incredibly low latencies all the way through.
Yeah.
Okay. Sorry for the interruption.
Oh, absolutely. The next thing I want to talk about is AI at the cutting edge. And this is the integration with IoT Edge. Maybe you've noticed this up here, this box right here. Here I have a server rack with 2 servers. There's a Dell and a Hewlett-Packard server there. And so basically now what we can have is putting these FPGA chips into these edge devices. And all integrated with Azure Machine Learning and Azure IoT Edge. So let me take a moment to talk about what Azure IoT Edge is. Azure IoT Edge enables you to compose the same type of pipelines you would have in the cloud and bring it to an edge machine. And so why would an edge machine be important? So as Doug mentioned earlier, maybe you have an oil platform out in the middle of the ocean. Maybe you have a super secret nuclear research facility and you have data that you don't want to touch the internet. Maybe you have those 1,000 cameras in your facility that you want to process without having to send all of that data to the cloud. So what Azure IoT Edge enables you to do is to compose various services and to containerize them in Docker containers. So your stream analytics, your Azure functions, or your own custom Docker containers can be incorporated with the IoT Edge runtime. And that would just be containerized, and then you would be able to bring that down to the edge. And now this is running on the edge device. You manage everything from the cloud. So for example, maybe you have 11,000 retail stores. So from the IoT hub in the cloud, you would manage all 11,000 of these edge devices. You would be able to configure and say, these are the models I want to run in Northern California. These are the models I want to run in the Eastern United States. You can configure that in the cloud. It's just a JSON document. And then you push all of that to the edge. The edge devices will then pull the containers from their respective registries to be able to bring down those containers, instantiate them, and run it. And so this enables you to be able to manage from the cloud in disconnected or non-connected or scenarios in which there's very, very little connectivity. So you're saving on bandwidth, you're saving on latency, you're saving on cost when you can bring this down to the edge. And so what this means now is the same types of integration could work. And so let's jump over to a different VM. And I know all the VMs are looking the same, but I'll show this VM right here, and this is an actual edge machine. So let me just pull up the device manager and just prove to you. You can see here that we have a Catapult FPGA device. So right here in this machine, in one of these edge machines, we have FPGA cards in there with an FPGA, and this is an actual FPGA in an edge device that you would essentially be able to deploy onto your on-premise locations there. And then the same type of app that I can run. So I'm going to open up this config file real fast. And just show here. This is the IP of that VM here, 10.123.88.134, right? So it's not I'm not making a call off the box. I'm making a call on the direct machine that's happening right here. So let me run the demo again. And it's the same app, except now it's running locally on the machine. And let's just start that running again, right? So same idea. So what's happening here is the same thing, except now the images are being sent, they're processed locally, and then let's kick it up a little bit more at the number of threads. There's still some things that we're trying to work. So basically what's happening with IoT Edge, because everything is container-based, we're sending images from a container to that API and getting it back. And so the latencies are a little higher. And throughput's a little different on this Edge machine. But same ARIA 10 FPGA, same type of architecture, and the ability now to be able to process mass amounts of data locally on your Edge device. So this is something that we are working with in a private preview. And so if you're interested in this type of scenario where you want to have that FPGA on an edge device on-prem, then feel free to reach out to us and we'll be able to chat with you more about it. So for us, I mean, like for the cloud server, about 8, and then edge device, maybe we should just kick it up a little bit more. There's some overhead with the containers. That's the main reason that we have to work through. And so really just to summarize everything we've talked about in terms of Azure Machine Learning. Azure Machine Learning, hardware accelerated models powered by Project Brainwave. We're really good at naming here at Microsoft, so you know exactly what you're getting with our names. But essentially, the models, as we had covered, easy to create just using Python and TensorFlow, easy to deploy into the cloud. Write once, deploy anywhere. everything that I ran through in that Python, in that Jupyter notebook with that TensorFlow code, the model that you create can be deployed to the cloud and also deployed to the edge without changing anything. So write once, deploy anywhere. Manage and update your models using Azure IoT Edge. So from that IoT hub, you can basically say, oh, data scientist created a new optimized model, works better. I'm going to push it to my edge devices. Now those edge devices have an updated model that are running on the FPGA. And so in terms of next steps, we'd love for you to just go check out our GitHub repo to just give it a shot and be able to deploy your own FPGA service and really just unleash the power of real-time AI. So thank you very much. So we have about 8 minutes left to take any questions. I'll invite Doug back up here and to be able to address any other questions that folks might have. Yeah. OK, let's start with a 2. Yeah.
I got a Mac already. The Brainwave, I really like the product, but the question is really about the Azure ML.
Yeah.
So for Azure ML, although I believe that the public cloud is the future, right? In the next maybe a few years, there are still a lot of customers using a private cloud. So do you think Azure ML could support them in some way? If yes, what's the roadmap? If not, what's the blocking issues?
Yeah, in terms of, so you're saying just a completely private environment that does not touch the cloud
Deployed
at all?
Azure ML at a private environment.
Yeah, so this is where we might want to talk about ML.net and also our server offerings. So Azure ML is a cloud offering that enables you to connect to experimentation services and to model management and different types of services that will help you manage all of that. But we have a whole suite of on-prem offerings that will also be able to run these things without ever having to touch the cloud. So those are things that we can talk about. Srikanth here is our engineering director for Azure Machine Learning, so I'm sure he has more context to be able to speak to that.
Yes, so in terms of working things on premises, certainly we have the ML server offering that has high performance algorithms, so you can use that. Also, the models you build in the cloud in Azure ML, they're all containerized, so you can actually take the container and run them on premises, and actually you can choose to send the telemetry into the cloud if you want, or if you choose not to. So those options also exist. And as Ted said, now the Azure IoT gateway and the edge devices are another place where you can run these models. So.
Thank you for the talk. For workloads that are bursted in nature, how long are we looking at to scale out and add new instances on the fly? If I realize I need more, I have more demand, how long does it take to increase capacity? Yeah, that's a great question. And so this is on the order of seconds. So basically what we have is we have a VM pool. Today, it's it's already flashed with a ResNet 50 image, and it's just a matter of copying your model file to it, spinning it up, and adding it to that load balancer. And so it is somewhat of a manual process today. We don't have the automated way of being able to detect higher traffic, so there will be some manual work that you'll have to do to basically increase that pool. But once you say, I want to spin up some more, then you'll be able to add more fairly easily. Yeah, a great question. Thank you. And to that point, what I also want to say is that from the experiences that we've had working with some customers in our preview, before GPU machines and CPU machines are so expensive that you want to be very, very cognizant about how many you're actually provisioning at a given time and to be able to try to scale up and scale down as you need. That's because they were just so expensive. In a way, the FPGA machines are so cheap. One customer, they just provisioned for their max, throughput, even though they may be only using this much at a time, and they may be using this much on bursty. And provisioning all of that was cheaper than doing it on a CPU or GPU machine, or GPU clusters. So that way, they didn't need to worry about it at all. It was even cheaper that way.
So maybe the elephant in the room, maybe not. I don't know if you addressed Brainwave addressing scaling for training the models. So when is that coming? And
get my my mic on here. So I don't know that if it's an elephant in the room, because Azure offers the leading edge NVIDIA GPUs today, which you can rent to train.
No, I mean, it was from the perspective of different silicon.
Yes, that's right. That's right. We haven't announced anything with respect to training at this date. So if there's an elephant in the room, I'm ignoring it.
I think a lot of people
They're certainly free to do so. But so today the answer is, rent NVIDIA GPUs or Intel CPUs in the cloud to do scale-out training, and if and when we have offerings that add value for our customers, we'll roll those out.
I mean, that would be really good cost value to bring to that side of the house.
Well, if you had something that provided good cost value, then we would bring that out to our customers. Yeah.
So the question is, what kind of hardware was on that drone that was introduced? Yeah, so we're actually working with a bunch of different hardware partners in terms of, when you talk about IoT, we actually have a session this afternoon at 4:30 where we're going to be focusing on IoT and Azure Machine Learning and all the various deployment targets for that. So FPGAs, and also we just also announced that partnership with Qualcomm and their chips, the 605, to be able to containerize the models and deploy them and accelerate them on the Qualcomm chips. And then in the drone itself, I think they were the GPUs that were running in the drone, as far as I know. Yeah, yeah, NVIDIA GPUs. Yeah. Yes.
So let me ask the question. So there are two questions. How is the FPGA connected to the PCs? Like, what kind of? Because you need a high-speed bus from CPU to the FPGA.
Yeah.
So is that like PCI Express?
Right, PCIe. I think it's Doug PCIe.
Yeah.
Yeah, PCIe to connect from the FPGA to the.
The other question is, what about having this work on a true edge device? Because what you have here is like on-prem. But if you're an industry that sells devices and you are not really in control of the premises, so as to speak, what would it take to make this work on an edge? Like FPGAs come in all sizes. You could, in theory, have it on a true IoT product. Are there some plans to provide this on those kind of fabrics?
Sorry, if you,
maybe I'd be happy to take this. So I'm happy to. The question is, are we planning to take this to lighter weight IoT edge devices, with potentially smaller FPGAs? And I would say that if you look at the other partnerships that we've announced in the containerized ML, really, Azure is going to be one of the very small number of global computers with just massive number of cloud hubs talking to billions and billions of IoT devices, and AI and ML are a central part of that. And so I don't think we want to be tied to one particular technology. What we want to do is be able to push the best AI we have to all of the endpoints. With this offering, what we're showing is that we can hit really differentiated high-end performance and cost in the cloud and on what I like to call the heavy edge. I don't think this terminology is really settled. And then when for other lighter IoT nodes, there's going to be, I think, a lot of churn in different technologies. And whatever ends up being the victor there, or the set of, when things stabilize, the set of technologies that get deployed, we will serve advanced ML models to those. So if we think we can do it with smaller FPGAs in partnership with Intel, for example, that would be a great offering. If it's other technologies, that may also be good. So I think we'll be agnostic. What we'll try to do is just make all of that better.
Yes. Yes. Yes, thank you, Rashmi. So there's a booth with working servers with real FPGAs in the servers that are actually working in the IoT Edge booth in the expo hall. So I think thank you, Rashmi, for reminding me something to see. And so we're running out of time, but the thought I want to leave you with is in terms of the direction that Microsoft is going with all of this. You probably saw the mail two months ago from Satya. I think you probably saw it on Twitter sooner than some of us saw it, just because of the time it took for all the emails to get through Microsoft. One of the main things that came out of that was the combination of a team in Bing, the AI platform team in Bing, and the cloud AI platform team from Azure. Typically, Microsoft as fairly schizophrenic, or maybe even with 27 different types of personalities. And what happens is, the Bing team are dealing with their Bing scale problems, and they have a set of tools and things that they're using for them. And then we make some some other set of tools for our end users and customers. And that just didn't make sense. And I think we're finally starting to see the light and organizationally combine so that this is one of those things where the same problems that the Bing team have been trying to solve, the tools that they're using, the technology that they're using, we are enabling and bringing out to you. And so this is one part of that. You're just going to see that more and more and more. And so we're super excited about just all of the great things that we can now bring to you as the end customer and as the end user. So starting with something like Brainwave and ResNet 50 to really help you accelerate and get real-time AI. So thank you so much for your time today.